Okay, alright. Welcome to the example for part 2. Okay, on the previous from the previous class, we know that we solve for the determine the pressure and the temperature at a new state. For those who are the first time here, actually this is a continuous for the previous class. The question say that a pressure cooker contain 1.5 mass at saturated steam. So this is indicate state 1. Find the quality of heat. So we're talking about Q here. Must be rejected. So it means must be cooling down. So they reduce the quality to 60% dry. So initially, okay, so all my P specific volume. First is at saturated steams, and in the class we know saturated steam is here. D is your critical point. From here, this line, so I'm going to change it to yellow. From this line onwards, this is your saturated steam. So I'm going to put as steam. And from here downward, saturated liquid. And then from this example, state 1 is like this here. And then state 2, is say about quality here. State 2 might be somewhere around here. So at this stage, we're not sure is either how's it. Okay, but what we know the pressure is not the same. Why? Because the question here state pressure and the temperature at the new state. So we can say that the volume V1 is equal to V2. So this is a constant that we use and to come up to these relations. So basically previously we done the calculation. P2 through interpolation we get 2.9 bar, and T is equal to 132.4 Celsius. So how you want to get to quality of heat? To get the quality of heat, first of all, so I'm gonna go to the new slideshow, new page. Okay, alright, so how to get Q? We know here Q plus W equal to internal U. And seeing this question talking about, first of all, volume V1 is equal to V2. So it's no volume displacement. As I told in class, when there are no volume displacement, it means Q W equal to 0. And in this case, heat transfer is equal to change of internal energy here in this case. So where is it equal to U2 minus U1. But in this case question as well, the temperature at state 1 P1 is equal to 5 bar. Meanwhile, pressure at state 2 is equal to 2.99 bar. So we know as well there are changes of pressure here. Even though volume is a constant, but there are still changes of pressure here. So in this calculation, you need to consider the pressure, and how to consider it will still relative to the internal energy. Still relative to this internal energy. Then we go to this formula. All we know, H is equal to U plus PV. And what is H? H is sample specific enthalpy. In this case, it's not capital H, it's specific enthalpy, specific internal energy, pressure, and here this one is specific volume. So I can say as well Q is equal to, okay, in terms of specific per mass, specific internal energy 2 minus specific internal energy 1. Can I say that? No, I can't, because if I'm saying this in this relation, is mean these two is changed. So what I'm going to do now is I'm going to erase this part, erase it. Oh, not. Okay. So what I'm going to do, Q is relative to its equation but still in terms of internally, u is equal to, okay, all of us is equal to H2 minus PV, because H2 minus PV is equal internal energy, in this case H2 P2 and V2 minus specific enthalpy, initial 1 minus P1 and specific volume 1. U internal energy, specific internal energy at state 1, specific energy at state 2. Q equal to U2, I just put it nicely here, is equal to H2 minus P2 V2 minus H1 minus P1 V1. But in this case, at state 2, all of you need to remember is under mixture. Is under mixture, and this one is at saturated steam. I put here, where pressure at this one is corresponding to 0.9 bar, pressure at here corresponding to 5 bar. So all about now the formula. So now we need to use this formula and this formula. We need to use for mixture. When you say mixture, you must have the density, or not have mix. We need to have the quality. In this case, the quality is 0.6 bar from the question. So we're going to proceed straightly to the calculation. Okay, as I said just now, we're going to do calculation at state 2, mixture. Okay, so specific internal U equal to, and specific internal enthalpy U, pressure, specific volume. Okay, and here I said, so I'm gonna put here, okay, first of all, what is the formula for enthalpy, specific enthalpy at the mixture? So V average, H average equal to HF plus X quality times HFG. Okay, and here according to the pressure just now, and I've done the interpolation, so I'm going to straightly put the figure. HF at 2.9 bar equal to 556.5. Okay, and unit is kilojoule per kg, and then here HFG is equal to 2166.6 kilojoule per kg. So, okay, VG2, this one is actually for specific volume, which we'll unit later on for the PV. I'm going to put here anyway, 0.625 power negative 3, because it's relatively small, and X for X2, so this one, the X for enthalpy, for the quality, 0.6. Alright, so I'm going to put here the color. So this is formula for the specific volume, this one formula here, and this one, the one is this. Okay, and then shall we put everything here? So U2, specific volume at state 2, is equal to HF. I'm going to put a long equation here, plus X HFG, okay, right, minus P2, and this P2 is 2.9 bar, and V2, volume 2. And this case, since we're talking about specific volume per mass, so T is corresponding to specific volume per mass, and end up you will got, so I'm going to put summary, 174.71 kilojoule per kg. So let me check my figure back. 1747 points here, 71 kilojoule per kg. Okay, so this one is specific internal energy. So if you want to convert it to specific internal energy, what you need to do, just time with 1.5 mass, because that is your mass. But we're gonna leave that towards the end. As for now, I'm gonna leave it in this form, in specific internal energy. So we're done at specific internal energy at state 1. So what is the value of specific internal energy at state 2? At state 2, it's relatively simple. Why? Because it's actually at the saturated, state 1, okay. Right now we want to solve specific volume at state 1 equal to H1 minus P1, 5 bar, V1, and here is lies at saturated steam. Okay, and the formula is all correspond to Hg. You need to remember here, all this mean H1, this one is Hg at 5 bar, and this one is Vg at 5 bar. Why? Because Hg, specific G, is mean energy, specific of enthalpy at steam. We just focus or interested on steam because again it's on the saturated steam. You do this point. So the formula here, Hg minus P1 and Vg. So some student ask me, will I need still to consider on the quality here? X2. Oh, sorry, pop up there. Why is this happening? I don't want this. Messy. And then come back. Sorry about that. Alright, so go back to my question. Some student asked me, at this stage 1, shall I still consider the quality? My answer is no, because the quality at this stage at saturated volume equal to 1. Meanwhile, all of us know saturated quality at saturated fluids is 0, and towards here at saturated steam, or some books refer to as saturated vapor, equal to 1. And the mixture is only applicable at mixture. So the quality only applicable during mixture stage, right? And then all figure you can get for the steam table directly is equal to 25660 kilojoule over kg. Why kilojoule over kg? Because this is still on specific internal energy, and then I got my specific internal energy 1, state 1, and specific internal energy at state 2. And what I need to do? I just minus it. How to minus it? Again, back to our formula just now. Q equal to specific internal energy 1 minus specific energy 2. But now we want to get in this condition, we don't want to get the specific internal energy, we want to get internal energy. So what to do? We need time with the mass. So here it will be like this. Okay. After you solve this calculation, you will end up with negative. Some students say, I got my value negative 18.43 kilojoule. And why is negative? Class, you need to remember, at state 1 is at saturated mixture. State 2 is in the mixture region, so perhaps 0.6 is here. So in order steam to change state from steam to mixture, the heat must be removed out. So is the energy or heat being removed out, cooling down, during cooling period. So since we are in thermodynamics, we are so good and so great, we are able to calculate that's actually the energy we remove the system from state 1 to state 2 is 1218.43 kilojoule. So basically you solve your question already to get up to energy is required for this system. Okay, then that is example for part 2.